Alright, today is the 15th. So, do y'all remember the equation for momentum? Momentum is equal to what? Our mass times velocity. We usually write mass first. So a steel ball whose mass is 2 kilograms is rolling at a rate of 2.8 meters per second. What is its momentum? So we write our given variables. Our mass is 2 kilograms. And our rate of speed, our velocity, is 2.8 meters per second. So we know our equation for momentum is equal to mass times velocity. So our mass is 2 kilograms. And our velocity is 2.8 meters per second. And so that is equal to 5.6. And our units is kilogram meters per second because it's mass times velocity units. So try solving number 2 on your own. Yes. And Cody, keep your mask on. Even though y'all say y'all can't breathe, it literally has no impact on your oxygen level or your CO2 levels. The only thing that it does is make it uncomfortable to breathe, not stop your breathing. Does anyone know why it's uncomfortable to breathe in a mask? Mm-mm. So you're right the first time, you're not used to it. That's the primary thing. Like for example, if you were to wear a wool shirt, you probably will feel very itchy and uncomfortable to wear, and you would probably walk around saying, "I can't wear this." An authentic wool shirt because it's not something you're not used to. CO2 it leaves the mask just fine. Oxygen comes in just fine. The only thing it really does is increases the moisture in the mask because you're breathing out a lot of water vapor, and this water vapor just makes it just feels uncomfortable. It's the same thing as being out in the rain while breathing, or having a humidifier pointed at your face. It would be the same level of uncomfortable if you stood next to a humidifier, which some people actually like to do. But the primary thing is, yes, you're just not used to it. Yes. And Thomas, keep your mask on. So Thomas, what'd you get as an answer? You should be working on it. So who has gotten an answer? Raise your hand. So what'd y'all get? So let's look at our given. So a marble is rolling at a velocity. So this is our velocity of 1.5 meters per second. With a momentum, so we use P for momentum, of 0.10 or just 0.1 kilogram meters per second. So we need to identify our equation. We could use a triangle. Momentum is equal to mass times velocity. And we're asking for the mass, and mass is equal to P over V. So this is over, or V. So it would be momentum divided by velocity. So that would be 0.1 divided by 1.5, which is equal to 0.066, 6 and 6, so on. And our unit for mass is kilogram. If you wanted to just write like 0.06 carried, that'll be fine as long as you put the carried. But I usually prefer you write out several digits. So 666. And then this would be a 6, but the one after it is a 6. So that causes that to round up to a 7. So conservation of momentum. Conservation of momentum is just another way of formally saying initial momentum is equal to final momentum. So the sum of momentum before a collision has to be equal to the sum of momentum after a collision. So suppose you are playing ice hockey in the middle of a totally frictionless frozen pond. How can you move yourself to the edge of the pond? So remember saying that the pond is frictionless, which means if you are on a frictionless surface, you're unable to push on the ground, so Newton's third law won't work. Because you're unable to push on the ground won't push back. Because how normally, if you're walking, the reason why you're able to walk is because your shoes push on the ground and friction pushes back, causing you to go forward. But if there's no friction, you would just slide. So with no friction, your hand will just move over the surface, and there'll be no way you can move. But what is another way you can move, even if there's no friction? Another way of thinking of this is if you're in outer space and there's no ground to push on, and you're holding a hockey stick and a puck, what is one way you can move in outer space? And Thomas, keep your mask on. Pushing against there is no air in space. But this assumes that there's no friction. What was you saying? So how could you move? So if you're in outer space and all you have is a hockey stick, how would you be able to move? There's no air to push. What could you do? There's no air to move. So the reason why whenever you're... Yes. So if we're in outer space, what could you do? So let's reword this problem as you're in outer space. So you're in outer space and you're holding a hockey stick. So you're not moving. What would happen if you took the stick and you threw it in this direction? You gave it some momentum. So the mass of the stick times the velocity of the stick is this momentum. Now, if you threw it in this direction, remember that momentum beforehand was 0 kilogram meters per second. So if you gave this some momentum, the total momentum has to add to 0. That means you must also have momentum in the other direction. So it'd be the mass of the person times the velocity of the person. And the velocity will be negative because it's going to the left. So if you were to throw your stick away, you would start moving because according to conservation of momentum, the total momentum has to stay the same. So 0 to begin with, that means that your velocity has to increase in the opposite direction. This could also be thought of as Newton's third law. If you throw the stick, you push on the stick's going to push back on you. So if you were still standing on a frozen lake, if the lake is frictionless, when you throw the stick, you would have to slide in the other direction. There's been actually a lot of movies where, for example, have any of y'all seen Interstellar? Interstellar, the movie about black hole and what's his name? Matthew McConaughey. Oh, that's a good movie. They're falling into a black hole, and what they do was they drop. They lose part of the cargo, or they throw the ship in. They get into a escape pod, and what they do is the escape pod blasts off of the ship. So the ship goes toward the black hole, and because of Newton's third law and a conservation of momentum, the ship has to be pushed away from the black hole. Interstellar. It's a really good movie. Yes. Um, there's been actually a lot of good science shows that use that principle. Like I forget what it was. Firefly, maybe. Persons in outer space. They ran out of propellant, so they're unable to move. So what they did was they took a deep breath, disconnected their oxygen, and just threw it. Because their oxygen tank was, they pushed on it, pushed it away. They were able to glide to the airlock, and while holding their breath, they opened the airlock and got back into the spaceship. Interstellar. I don't know. I don't remember the name of the other movie. I think it was Firefly, animated series. Not animated series. Sci-fi show. I don't remember if that was the show though. It was in like during the pilot. So let's work on this example. A 4.5 kilogram ham is thrown into a stationary 15 kilogram shopping cart. At what speed will the cart travel if the ham had an initial speed of 2.2 meters per second? Do y'all remember how I set these problems up from yesterday? Try solving it on your own. I'm pretty sure I did.
Okay, it may be glitching again today. On my end, it showed you didn't, but that's the way it did yesterday, too.
Alright.
Just double check for me to make sure you did, just in case.
If you give me a second, I'm loading it up.
Okay, thanks.
Yeah, it showed. If you're still there, it showed me mark them. Yes. So, did y'all get an answer? So, we have a ham that has a mass of 4.5 kilograms, moving with an initial speed of 2.2 meters per second. And we have a stationary 15 kilogram shopping cart not moving. Afterward, we have a 15 kilogram shopping cart with a 4.5 kilogram ham, and it's moving at some speed. That's what we're looking for. At what speed? I'll call it V. So now we need to figure out total momentum. Total momentum on this side would be equal to just the momentum of the ham. 4.5 kilogram, the mass, times the velocity of the ham. And we can go ahead and do this. 15 kilograms is stationary, so the speed of the shopping cart is 0. 0 times 15 is just 0, so that cancels out. And so we get a total momentum on the left side as 9.9 kilogram meter per second. The total momentum on the right side would be the total mass, 15 kilograms plus 4.5 kilograms, and they're moving at some speed v. So that would be 19.5 kilograms. What's up? Yes. And that's equal to 19.5. So here, we can set both sides equal to each other. That's 9.9 on the left side has to equal the right side, which is 19.5 times velocity. So we take this number and divide it by that number. Or if you want to do a triangle, we know that 9.9 is equal to 19.5 times v. Solving for v is that over this. So 9.9 over 19.5. And that is equal to 0.50769. And they're looking for speed or velocity. So that would be meters per second. By the way, always include the leading zero. Whoever told you it's appropriate to just put 0.5, that's wrong. You should include a zero before it. I might. Everyone good? So try doing number 5 on your own. This one's different. I don't think you'll be able to use a triangle. So this one's going to be more challenging. For remote learners, here's the code word. This is the code word for remote learners. And this first ball and ball is going to be ball 1. And this is ball 2. Anyone get an answer? What'd y'all get? Very good. Not miles, though, meters. So this one's more challenging. So we have one bowling ball, it's 6 kilograms, moving forward at 5 meters per second, and hits a stationary 4 kilogram ball. Afterward, they don't stick together. Instead, the 6 kilogram ball slows down to 2 meters per second, but the second ball, which is 4 kilograms, starts moving forward at some speed. So you can think of this kind of like billiard ball pull. So you have a cue ball, hits another ball. The cue ball continues moving forward, but the ball it hit starts moving at great speed. But the general strategy is still the same. We need to find total momentum. So the total momentum on this side would be 6 kilograms times 5 meters per second plus 4 kilograms times 0 meters per second. And so that's 30 kilogram meters per second. On this side, they're not stuck together, so we don't add the masses together. The total momentum is equal to 6 kilograms times 2 meters per second plus 4 kilograms times velocity. So this would equal 12 kilogram meters per second plus 4 kilograms times v. So we have an additional term on this side. There's some momentum added to this momentum. To solve for this, and let me bring it down here. I'm running out of room. So the total momentum would be 30 equals 12 plus 4 times v. That is our equation we came up with. This 30 has to equal, so the total momentum on this side has to equal the total momentum on this side. So we have 30 equals 12 plus 4v. So I can subtract from both sides this 12. So let me subtract 12 from this side and subtract 12 from this side. So 30 minus 12 is 18. 12 minus 12 is 0. So 0 plus 4v. And we can just remove this 0. So that's 18 is equal to 4v. And now we can divide both sides by 4. Or if we have it in this form, we can use the triangle. So that's 4 times v, 18. So we can just divide by 4 on both sides. This would be 18 divided by 4 is equal to v. Our velocity is equal to 4.5 meters per second. So in this example, which is slightly more complicated than the normal examples I've been giving y'all, they don't stick together. They continue moving independently of each other. Sticking together just makes it more easier, so we don't have to subtract this additional momentum for both sides. We only end up with one momentum on the right instead of 2 momentums. From the top. So, ball 1, what it does first is hit ball 2. And what ball 2 does first is get hit by ball 1. If ball 1 hits ball 2 must be hit by ball 1. When it hits ball 2, what it's going to do is lose momentum. So it's going to loses momentum. Actually, I made a mistake. Looking at the writing in pen. Forgive me, I'm writing in pen too. Looking at all these terms, starts rolling would be better. No, it's not. The first thing is, rolls would be the best thing, is rolling. It rolls, and then it hits ball 2, and then it loses momentum. This one is resting, so it's rest, and then it is hit by ball 1, and then it starts rolling. And this would technically, this would be slows down. And now it loses momentum. Actually, no, I had that right to begin with. It doesn't really matter. These could be switched in anyway. It would be loses momentum first. And because it loses momentum, it slows down. And this would be gains momentum. This would be starts rolling. Yeah, the order of this is, sorry, I didn't think this through. Starts rolling and gains momentum. And this would be slows down. This is slows down. I'm trying to match both sides, and this would be loses momentum. When you're slowing down, that's the same thing as losing momentum. So these could have went in any different way. Sorry for the mess. These could have been swapped around. Either way would have worked. And these could have been swapped around. So let's work on some more examples together. What was that? Yes, they're notes. So let's do some changes to this problem. A 4.5 kilogram ham is thrown into it's different, into a 15 kilogram shopping cart that is moving. The ham is thrown at 10 meters per second. Super fast. The cart and ham together. I'll say thrown to the right. Thrown to the right. Move together at 1 meter per second to the right. How fast and what direction was the shopping cart initially moving at? So a 4.5 kilogram ham is thrown to the right into a 15 kilogram shopping cart that is moving. The ham is thrown at 10 meters per second to the right. The cart and ham together move at 1 meter per second to the right after clotting. How fast and what direction was the shopping cart initially moving at? So you don't know the direction and speed of the cart. That's what you're looking for. Can y'all solve it on your own? Yes, it's thrown to the right. So I'll just go ahead and set it up. We have a ham. Its mass is 4.5 kilograms. It is being thrown to the right at 10 meters per second. We have a shopping cart that is currently moving. So this is the before. And afterwards, we have and this is 15 kilograms. And a ham now in it. And the ham was 4.5 kilograms. And together, they are moving to the right at 1 meter per second. The question is, how fast was the shopping cart moving at? What? No. It says clearly the shopping cart that is moving, so it's moving. It's completely different. It's closer to problem 5 than it is problem 4. Oh yeah, I just reworded it. So if you don't know the speed of something, I'll go ahead and solve this. If you don't know the speed, assuming that it's moving in the positive direction. So I'm going to let positive be to the right, negative be to the left. So I'm going to assume that this is moving to the right at some speed v. So we need to look at total momentum. Total momentum would be 4.5 kilograms times 10 meters per second plus 15 kilograms times the initial speed of the shopping cart. And that has to equal the total momentum on the right. The total momentum on the right would be the mass, 15 plus 4.5 kilograms, times the speed of 1 meter per second. So simplifying, this 4.5 times 10 is 45 kilogram meter per second plus 15 kilograms times V. It'd be 45. 10 times 4.5 is 45. So multiplying these together, just bringing this one down. We add the masses. So that would be 15 plus 14, 4.5. That's 19.5 kilograms. So 19.5 kilograms times 1 meter per second is just 19.5 kilogram meters per second. We can remove units to clean it up, or you can just ignore them altogether. 45 plus 15 times V has to equal 19.5. So we have two terms on the right. We need to get rid of the 45, and just like last time, we're going to subtract 45 from both sides. So I need to get rid of right here, so I subtract 45 from both sides. Yes. If you take an algebra, this would be a lot easier, but again, I'm not teaching you. But you can subtract 45 from both sides to get rid of it right here. And you're left with 15V equals negative 25V. Yep. So V would be equal to negative 25.5 over 15. And so that equal to negative 1.7 meters per second. So what this negative means, because we assumed it was positive to begin with, it means that the shopping cart was initially moving to the left. You can just go watch the video the last 2 minutes. And that's it.